Awesome. Good morning, good afternoon, good evening, wherever you are joining us in the world. Welcome to our first live stream with the AI research team. I'm really excited to be here with some of our team members to talk about SwiftKV and ArcticTraining and some of the really great work the team has been doing for optimizing LLM inference and training and distilling LLMs. As we get started, if everyone wants to just put in the chat or in the comments where you're joining in from in the world. I'm Josh. I'm a developer advocate here at Snowflake, and I want to first start by just introducing the rest of the team. So Rita, if you want to bring in the team, and we can get started with that. I see Jeff first, so maybe Jeff, do you want to give an intro about what you're working on and a little bit of your background?
Sure. Thanks, Josh. Excited to be here today. But yeah, my name is Jeff Rasley. So I joined Snowflake about a year ago. Came from the Microsoft DeepSpeed team, one of the co-founders of DeepSpeed over there. And lately been working on all sorts of exciting things around AI research topics that Snowflake cares about. So currently, SwiftKV was a big focus, and then now post-training related stuff. Can you hear me good? Okay. Thanks. Maybe I'll pass it to Zhewei or Aurick.
Sure, thanks, Jeff. Hello, this is Zhewei. I joined Snowflake about like 14 months so far, and I actually joined like probably a few weeks earlier than Jeff. So I'm from like Microsoft as well. I'm working on like modeling side of AI, mainly on like compression, pre-training, post-training, and other things. Very nice to see everyone. And now I pass to Aurick.
Thanks, Zhewei. So my name is Aurick. I've also been working with the Snowflake AI research team with Jeff and Zhewei and many others. So mainly I've been working on optimizing LLM inference in the Snowflake Cortex product and making it cost efficient and performant for all of Snowflake's customers.
Looks our MC is dropped.
Yeah, I think Josh is rejoining here, but cool. So I think today we're going to be talking about two major topics. So one is on SwiftKV, and the other, and all the optimizations kind of relating to that, and what SwiftKV is, how you can use it inside of Cortex. And then the other main topic today we're going to talk about is ArcticTraining. So this is a framework that we've built and open sourced that you can use today to kind of build your own SwiftKV models or other sort of types of models that we've open sourced through this framework. I don't know if Aurick, you're able to share your slides and we can just kind of dive right in.
Oh, okay. So it looks like the slides are up, which is great. So I'm going to give a brief overview of our work on SwiftKV first, and then we'll jump to Zhewei for a demo of SwiftKV in the Cortex product. And then Jeff will go over the ArcticTraining framework that we use to actually build SwiftKV, and we're releasing so that everyone can kind of build similar models as well. So in Snowflake, in our research team, we care a lot about making our LLM inference efficient for all of the Snowflake Cortex customers, making it cost-effective to run, right? And one of the first things we noticed is that in all the enterprise use cases that we serve, there tends to be a lot more input tokens that are processed than the output tokens. So the input tokens are those tokens that you would put into a prompt like the instructions, but it also include information and data that you're bringing in to LLMs like retrieved documents and so on, right? And these kind of this property is very broad across a lot of different enterprise applications, like text classification. If you think about that, you're reading a lot of text, and then you're just outputting one or two tokens that decide what the text is. There's sentiment classification, retrieval augmented generation, summarization, and a whole slew of different enterprise use cases all have this property that they're processing a lot of input tokens. Right? So if we can reduce the cost of processing input tokens, then we can bring that cost reductions to all of the Cortex LLM inference customers. So the key idea behind our research here is called SwiftKV. And the core idea is actually very simple. You basically take a large language model, which is comprised of many different layers that each token has to propagate through. And what we're going to do instead is we're going to take all the tokens and we're going to take the input tokens, and we're only going to use the first half of the model for the input tokens, right? And actually, it's surprisingly resilient to this kind of change. So in SwiftKV, what we're doing is we're taking a existing language model out there, like Llama 3.1405b, Llama 3.370b. We're applying a transformation to that model so that it's able to exit the input tokens earlier in the model. And now we have this model with a slightly modified architecture that's able to save the compute for input tokens. However, if you just do this, the model is going to have some accuracy degradation. So we have an additional step where we distill the transformed model from the original version of the model. And that allows us to recover the accuracy of the final model to a reasonable degree. And so this is just like a very brief overview of SwiftKV, and we have a research paper on this that's on arXiv if anyone's interested in the finer grained details of how we actually achieve this and the step-by-step instructions of how you can replicate it. Then there's the research paper in that link. All right, so with SwiftKV, so basically on the left-hand side, we're able to very closely follow the original model's quality. So, oh, is there some? Okay, so for example, for Llama 3.370b, we're able to bring the accuracy to around a 0.1% margin on average across a variety of different benchmarks. And on Llama 405b, we're able to bring the accuracy to within a 1.5% gap. So they're actually very quite close in quality to the original models. But on the other hand, on the right-hand side, we can see that the SwiftKV versions of the models actually can achieve much higher throughput in terms of the number of tokens that they can process per second. And this translates to cost savings for Cortex LLM inference customers. So the SwiftKV models are starting to become available in Cortex, and anyone can start to try it if you're on the AWS West 2 region. And at this point, I would like to hand it over to Zhewei, and he'll give you just a brief demo on using these models.
Thanks, Aurick, for the great introduction. So next, I will show you how you can play with SwiftKV models and how good is the performance. So I already logged into my Snowflake like AI ML studio, and you can find it easily from the left panel, like AI ML, and you click the studio, and there's Cortex Playground. This is so good to be like to do demos and try some simple ideas. And if you click try, and then we are logging in. And on the middle of the screen, you will see, oh, there's some list. You can like look for like Cloud 3.5, SoNet, Gemini. And if you go down, you will see the Llama families. Llama 2, Llama 3, Llama 3.1, and so on and so forth. And at the end, you will see Snowflake Llama 3.1 and
Sorry,
Snowflake Llama.
Can I just stop you and ask you to zoom in a bit so folks can see?
Sure.
Awesome.
Of course. So you will see like different Snowflake models. And today we will use another good feature in the playground. You will click the play, like compare. And okay, you have left and right screens. And on the left-hand side, we will choose the original Llama 3.1405b, the largest model from Llama family. And on the right-hand side, we will choose our Snowflake equivalent Llama 3.1405b. And I want to create any prompt by myself. So I will just choose something from some open source libraries or open source data sets. One is from the math data set, people call it GSM-HK. It's actually from OpenAI. And I will just randomly pick one. So you can see I'm definitely randomly pick one. I didn't choose anything. And let's do this one. I hope our model gives the correct answer. So if it didn't, don't blame us. So I copied the text and I paste it here. Now I click hit.
That's a lot faster. Very cool.
Yeah. But actually, on the left-hand side is the original llama, and it has a streaming like setting, and on the right-hand side we don't have a streaming thing. And the first thing, let's compare the output. The output is okay, like 48 is 48, and the final answer is 48. The final answer is 48. As you can see, the answer is definitely correct. However, the process is slightly different. On original llama, it has 4 steps. On the right-hand side, we have 8 steps. But sometimes they are very close. They have similar steps, and the thing are almost the same. Sometimes they have a different output because, as Aurick said, we distill the model, so the weights of the model are slightly different from each other. So it is expected. And next, I will give you another example. It's from the MMU. It's a high school statistics. You may wonder why I always choose math problem, because it's easy to compare like the final answer is correct or not. So again, let me randomly pick one. So let's pick this one. Let me actually clear the and for easy for comparison, and then paste their choices. And see which one is correct from the list. Now hit. So as you can see, her procedure makes use of the chance, her procedure makes use of the chance, and also the output is very similar to each other as compared to the previous one. Here is the correct answer. The correct answer is blah blah blah, and it gives 3. Why the other 2 questions are incorrect. Here is why. So as Aurick said, the performance-wise, the model of SwiftKV Llama and the original Llama are very close to each other. And you can always try it out in the playground, and you can also try it in your daily Cortex completion functions and other things. And we are very welcome everyone to try it out and give us any feedback. It's good, it's bad, it's faster, it's cheaper, all those things. Thanks a lot. So next, I will hand it to Jeff about ArcticTraining.
Yeah, I guess before we get to ArcticTraining, I think we've got a couple of questions from the audience about SwiftKV. So we have this question for closed source models like Claude. Can you use SwiftKV and apply some of the same transformations and distillations for those closed source models?
Yeah, so I guess I can take it. So currently SwiftKV only works for open source models to which we have the weights. So how it will be usable for users of Snowflake is that there's actually going to be different versions of those open source models, right? So we both offers the original Llama versions like Llama 3.170b, and then we'll offer a Snowflake version of it called Snowflake Llama 3.170b, and that's a different version of the model that's optimized using SwiftKV. And now for the original question for closed source models, yeah, for a lot of those models, we don't have access to the weights, so we cannot offer the SwiftKV versions for those.
Awesome. Yeah, thanks for the answer. I think from here, maybe we can pass back to you, Jeff, to give us a little bit of an intro on ArcticTraining and
Sure.
some of the research behind it.
One other thing I think I'd follow up on your answer there, Arc, too, is I know the question was on closed source models, but other open source models, I think we've also experimented with SwiftKV and saw good results. I think I'm not sure what the status is on open sourcing some of those, but I think we probably will be able to open source some of those, for Mistral and other sorts of models. I know that we've seen success, so that's might be something people are interested in. One other thing I think that we haven't talked about on the open source side that I just want to briefly touch on is if you go to Hugging Face, I think we're going to put some links in the chat. We have uploaded several of these SwiftKV model checkpoints, so you can try these out from an inference perspective, even if you don't have the GPU capacity to actually do the training yourself. But if you do have GPUs, this is where ArcticTraining kind of comes in. So what you see here is our blog that we released about a week or so ago on ArcticTraining. And what ArcticTraining is at the high sort of level is it's a post-training framework that we developed after a few different observations that our team has had on creating research prototypes and research ideas, essentially like SwiftKV. So SwiftKV was a central motivating sort of point to create ArcticTraining. We wanted to be able to have full control over how the model's created and instantiated, which sort of parameters are frozen, which ones we want to add in, which ones we want to train, defining loss functions, all the sort of core pieces that are necessary to train a model like SwiftKV models. And then other sort of types of models that we're also experimenting with, like speculative decoding models and like just basic like SFT style training, reinforcement learning style training, these sorts of things, like all require some level of experimentation from the research side. And what we've found is a lot of the existing frameworks are very well built and very well supported in the sort of ecosystem of all sorts of different types of backends. These things support, let's say, DeepSpeed and FSDP and bits and bytes and all these new sort of frameworks as they come out, which is wonderful if you want to experiment with those. But from our perspective, we're very focused, I think, in terms of what types of backends we want to support. Many of us come from the DeepSpeed team, so we want kind of deep integration with DeepSpeed. But that kind of led to the development of ArcticTraining. So some of the core principles here is we wanted to create a framework that was flexible in terms of the trainer design. So this allowed us to easily sort of modify and rapidly prototype different research ideas and new algorithms with sort of minimal effort. We also wanted a kind of a simplified code structure to allow us to kind of create these prototypes and also allow sort of a common functionality that a lot of trainers do have in terms of callback functionality. So we can inspect different points in the training stack. We can add logging. We can add some mutations of state, these sorts of things like in the actual like training loop. The other kind of core piece to ArcticTraining that we won't get into a ton of details here today, but I urge you to check out on our website and our repo is in data generation. So one of the core kind of pieces for post-training is often synthetic data generation. And what we found is there's not a whole lot of frameworks that kind of help you and ease some of the burden of actually creating some of this data. So we've released a whole pipeline here inside of ArcticTraining that allows you to actually leverage existing models, either a sort of a wide selection of models, either maybe running through Cortex or locally on your own machine to actually do that synthetic data generation. Okay, so in terms of architecture of ArcticTraining, we have the sort of the core kind of trainer component, and then all of these subcomponents, as you might imagine, if you've looked into kind of any of these trainers before, there's pieces in terms of how do you build the model, how do you get data into actually do the training, how do you handle checkpointing and tokenization and all these sorts of pieces. Each one of these are extensible, which we'll talk about shortly, but Arctic synthetic, or so the synthetic data generation is one of these core components as well, as you can see from this diagram. So you can kind of generate that data and feed that into your actual trainer. Each of those pieces, like this is the model factory shown here, kind of have these three main components of attributes, properties, and methods that you can customize and override and do whatever you want to sort of customize all those sort of pieces. And at its core, almost the sort of hello world, if you will, of trainers is like at this point is an SFT style trainer, supervised fine tuning. So this is kind of a good example of what this looks like to do basic SFT training. The front end is a YAML-based front end. So this is an example of one way that we would actually run this. We'll get into the code as well here in a second. But this YAML essentially defines the model that we're going to be pulling in. So in this case, we're pulling this in from Hugging Face. Data sources, we're also pulling these in from Hugging Face's datasets library. The specific DeepSpeed features that we want to use. So in this case, we're using 0 stage 2. And microbatch sizes, learning rate, sort of all the hyperparameters that you might want to specify, and then how you want to do checkpointing. There's a whole list of others as well that I'll should point you to the documentation here shortly. Data generation, whole set of customizations as well that I urge you to check out. But in terms of SwiftKV, so we have two examples in the blog. One is SwiftKV trainer, and then the other is speculative decoding. We're going to go a little bit into SwiftKV since we've already talked about kind of what SwiftKV is and the motivation. But instead of looking at the blog, let's actually look at the code itself. So the code can be found on our ArcticTraining repo. So this is on GitHub. Urge you to check it out. We also publish ArcticTraining to PyPy, so you can do a pip install of ArcticTraining to kind of get started, especially with the SFT example. If you want to use any of the advanced kind of projects that we've talked about here, so SwiftKV or the speculative decoding, you do need to check out the repo. Those are all under this projects folder here, and I'll show those shortly. One thing also I urge you to check out is link here is our documentation. So we have a whole host of sort of quick starts and documentation here to kind of get you started. in terms of all the different sort of configuration options that you can kind of use and leverage in this YAML are all documented here as well by the subsections of the subcomponents that we have. So like for data, for model loading, for optimizers and initialization, all that kind of stuff. Cool. So I've already checked out the repo here. This is NVS code attached to a machine that we have that has a terminal here. This has 8 H100s. So when we did the SwiftKV training for Llama 8B, we did this on 8 H100s. Excuse me. So in projects, we see SwiftKV, there's a train.py, which is what this is doing here is it's actually creating the specification for SwiftKV. So for example, there's a few hyperparameters. So we define a sort of config associated with SwiftKV. We define how to actually create the SwiftKV model. So this is actually being done from the Llama 8B and then specifying which components need to be frozen and which ones need to be trained and so forth. And then if we scroll down, there's a few other config components here as well to training. But then the core here is the actual loss function and then registering each of those config and model factory and checkpoint components here. And that's about it in terms of what needs to be defined for SwiftKV. Here is the associated YAML. So in this case, yeah, we're building off of the Llama 8B instruct model. And then we've experimented with all sorts of different data sources here, and you can kind of, we leave that up to you in terms of which data sets you want to sort of specialize or sort of focus on. And then I'm going to kick off an actual training, but I've set this logger level to info. So this is actually going to be quite verbose, but I can show you kind of what's happening along the way. You can also turn this to less by default, so it's a little bit more quiet. Okay, so to actually kick off the training, what we can do is, this is the ArcticTraining CLI. So what this is doing is it's a very lightweight wrapper over the DeepSpeed launcher. If you've used the DeepSpeed launcher before, you'd be very familiar with this. We can actually pass in arguments here to DeepSpeed launcher to configure, let's say, host files if you're doing distributed training, or number of GPUs you want to, like a subset of GPUs you want to train on. But by default, it's going to use all the GPUs that are on that local box. So if we hit enter here, what this will do is it will initiate the DeepSpeed launcher, which is going to launch 8 processes across all of these 8 GPUs, H100s that we have. Let me make this a little bit bigger here. Cool, so it's starting the launching. And this, I did this a little bit earlier. It should take about 2 minutes end to end, I think, to actually get started to train. But we can talk through, I think, a couple of the key components that are happening along the way. So we see we're world size of 8, so we're using all 8 of our GPUs. And here we go. So let me just scroll up a little bit because we missed a couple things. This is actually what this is doing here is it's actually being nice and verbose in terms of all the actual runtime configs that are happening in ArcticTraining. So we can see what tokenizer it's picking up, the actual data configs, the max length that's being used here, you can see there. Lots of, if we're using 1DB, we could sort of see how that's configured. The actual DeepSpeed config that's being passed in as well, checkpoint, so forth. There's also a lot of things here in terms of all the callbacks that are registered, so you can kind of see like which things you've actually registered with respect to callbacks. This is the actually the Llama config that was used. Okay, we loaded the checkpoint shards onto all the GPUs, and then in this case, this is just a warning from Hugging Face, essentially saying, hey, you have uninitialized weights, which is a good thing in our case because we're actually going to actually train on these SwiftKV weights. Initialize our optimizer, and this is now getting into DeepSpeed logs. So this is initializing 0 stage 2. So the optimizer states are being sharded across all those 8 GPUs to save us lots of nice memory. And this is all DeepSpeed configs. And let me just go down and maybe skip a little bit of this. And we're actually training. So we see train batches here. It's training for about 4,000 steps. Of course, we won't wait that long today, but we can see the the different losses that are actually being outputted for the SwiftKV training. And with that, I think we concluded the demo.
Awesome. So now that we've seen kind of a glimpse into the workflow, can you like double click again on like what using ArcticTraining trainer gives you versus just using DeepSpeed alone?
Oh, good question. So I think what we found, at least in developing DeepSpeed, is DeepSpeed's really nice, I think, as a training backend in terms of just adding value in terms of system optimization. So like these are things like memory reductions and all sorts of those sort of nice features that DeepSpeed provides. But as a front end, there's a lot missing. So what we've seen is there's like Hugging Face Trainer has kind of built a front end around DeepSpeed. PyTorch Lightning has done this. Axolotl's done this. Like countless sort of front ends have kind of been developed around DeepSpeed and other sort of training backends. So I think what the value here primarily is reducing a lot of that boilerplate sort of front end pieces that connect the actual models that you want to train. For post-training specifically, this is nice because there's tons of open source models that exist that you want to do post-training on. And Hugging Face is essentially the place to kind of pull in those models, right? So connecting sort of the common ways to access models with the common system optimization backends to kind of smooth out that experience, I think is the biggest win.
Awesome. I really love that you're thinking about the developer experience first. That's really cool. Well, I think we got a question from the comments as well. So there's a question that says, can you ask and share some stats on the input token reduction percentage range and like how that trickles down to the total cost impact? So maybe this is more of a SwiftKV question.
Yeah, I could take that. So from a modeling perspective, if you just look at the SwiftKV model, the reduction depends on how many layers that the input token actually flows through, and that's something that we can play with. So what we found is that typically you can skip up to 50% of the later layers without incurring too much of an accuracy gap. So at the fundamental level, the model computation for input tokens is reduced by, could be reduced by up to 50%. Now it's not a number of tokens reduction, but it's more of a amount of compute spent per input token, right? And in terms of when it gets to the Cortex product, we're passing on the vast majority of those cost savings to the customer as well.
Awesome. And I think just as we wrap up, it'd be great to talk about some of the research directions the team is taking in the future. So if maybe each of you can take a quick turn about like what you're excited about and some of the innovations you're working on.
Sure. Yeah. Excuse me. I'm happy to go first and then pass it to the rest. So I think like with ArcticTraining especially, is I think there's lots of areas to grow this framework and lots of new fun sort of areas I think that will be coming soon. I think one of the first big pieces that I think will be great to tackle is long sequence training. For example, on the DeepSpeed side, we released a project called Ulysses, but this was primarily built on top of Megatron DeepSpeed, which is a nice framework for pre-training, but it's not necessarily a great framework, honestly, for post-training. Mostly because like you have to pull in these models, let's say from Hugging Face, and adapt those to Megatron style. So like smoothing that path, I think is going to be a nice thing to do. Other sorts of training paradigms, I think, as well, will be added on top of ArcticTraining as well. But I'll let others maybe talk about that as well.
Yeah, let me go next. So we will working on like the post-training techniques, particularly for IOHF and DPO related stuff. And also there will be something related to like rack systems, like how can you do retrieval augmented generation better and all those things. And we plan to release something like in February, so stay tuned.
Yeah, and for me, I think one of the immediate things that we have been working on and we'll continue to work on in the future is speculative decoding, where we're not only reducing the cost of input tokens, but also speeding up the rate that output tokens can be generated. But in general, I think I'm excited about catering research, like any research that's very specific to Snowflake customer usage, because I think a lot of enterprise queries have a kind of different distribution than what a lot of the broader research community really targets and works on. One thing we found is that text classification is actually like a super popular use case, right? But if you look at the broader landscape, there's actually not a lot of work on specifically like targeting those kind of use cases that are important for enterprises, but maybe not so flashy when it comes to chasing AGI and that kind of stuff.
That's awesome. Well, I think with that, this wrapped up our first live stream. So thank you to everyone that tuned in, and for all of you guys for joining this live stream. It was a ton of fun to get into the details of some of this great work you've been working on. I encourage everybody to go check it out. The model checkpoints on Hugging Face, read the blog, and go try it yourself. Thanks, everybody.
Thank you.
Thank you, everyone. Bye.